Good morning, I5 Space. Thank you to everyone who is joining in on the I5 YouTube channel or I5 website. And thank you to Professor Sara Seager for joining us today. I'm Nicole Heselton, I5 STRAT Talk Program Coordinator. And today we are delighted to have a very special guest for our talk, MIT Professor Sara Seager. Professor Seager is an astrophysicist and a professor of physics, a professor of planetary science, and a professor of aeronautics and astronautics at the Massachusetts Institute of Technology, where she holds the class of 1941 professor chair. She has been a pioneer in the vast and unknown world of exoplanets, planets that orbit stars other than the sun. Her groundbreaking research ranges from the detection of exoplanet atmospheres to innovative theories about life on other worlds to development of novel space mission concepts. In space missions for planetary discovery and exploration, she was the duty science director of the MIT-led NASA Explorer class mission, TESS. She was PI for the JPL-MIT CubeSat ASTERIA, and she is the lead of the Starshade Rendezvous Mission, a space-based direct imaging exoplanet discovery concept under technology development to find a true Earth analog orbiting a sun-like star. And most recently, she leads a team working to find out whether or not the Venus atmosphere can support life. Her research earned her a MacArthur Genius Grant, and in addition, Professor Seager is an officer of the Order of Canada, a member of the U.S. National Academy of Sciences, and a recipient of the Magellanic Premium Medal, and has asteroid 9279 named in her honor. Professor Seager, thank you so much for being here today.
Thanks for having me today.
Our first question of the day is, what got you into studying exoplanets?
Well, I always loved the night sky and all the stars, and I hope you and all the viewers, if you haven't already seen a dark sky away from city lights and away from the bright moon, that you have a chance to, because it's just, wow. I always loved the stars. Then in high school, I studied physics, which was hard. But you know what? I realized that physics can describe the world around you with equations. And as soon as I learned it could help us answer brand new questions about the stars and beyond, I was hooked. And I went to graduate school to study to become an astronomer. And right around that time in the mid-1990s, exoplanets were first discovered. So I jumped on the chance to work on them.
Thank you. Our next question actually deals with your background and your transition between undergrad and postgraduate education, as well as your transition into research. Could you talk more about how that process went for you? Do you have any advice for those willing to go down a similar path as you did?
Well, the general advice is find something you love doing that you're also good at, and something that pays the bills. If you can somehow wrap all that up, you'll be doing well. So the transition is like taking opportunities for jobs, summer internships, projects offered at your college, just things like that that appeal to you, but are also aligned with your current job or education. So that's the first thing to keep in mind. The second thing is, if you get a job offer, say it's graduate school or a job or a posting that's really outside your comfort zone, take it. Because part of the journey is growth, and that takes to be a bit scared and outside your comfort zone. So it's a real mix of opportunity, luck, and the ability to take opportunity.
Perfect, thank you. Our next question is more for our viewers who aren't familiar with CubeSats. Could you talk about what they are and what your work on them was like?
Yes, I can. Well, traditionally in the past, access to space is hard. Like there's custom one-off space satellites made. Many nations, other than the US, small countries, they're not able to get to space. But an educational institute decided to try to change that by making a standardized form, a CubeSat, a cube that is 10 by 10 by 10 centimeters. And you can imagine stacking those cubes have 10 by 10 by 30 centimeters or bigger. And I wasn't there at the time, but I'm guessing the point was that if you could have a commercial infrastructure built around this, you could buy parts that had been flown already and therefore not have to design things from scratch. And this has opened up space to a huge range of people from these smaller countries to educational institutes. Probably wherever you are has had a project of students building CubeSats. Now, okay, sadly, a lot of them fail. They fail when they get to orbit. They fail at the interfaces, because if you're buying components and making them work together, obviously that's what your job to do, and that's a really hard job. But on the whole, it's really changed it's really changed access to space by making things cheaper and more accessible.
Do you
So,
see the CubeSats developing in a different way? Like, do you see them becoming cheaper in the future, or do you see them becoming more complex? What do you
good
see
question.
about
I mean,
CubeSats?
initially people thought they were so cheap, but what they hadn't realized, if you want to do sophisticated monitoring or science in a small package, it actually becomes more complex. So it's true smaller and lower mass is cheaper, but it's also true that more complex is also not cheaper. So I think things are mostly still shaking out, but there's still a high value in having a uniform standard. I think in the ideal world, that standard would change. It would be bigger and it would be driven by capability, not just by, 10 by 10 by 10 centimeters units thereof. So I think it might have to change, but I think it's all still shaking out now. I mean, instead, really, you're seeing larger companies. I mean, the extreme example is Starlink putting up the constellations. They have their own standard, so they can just mass produce things. But we'll see.
Thank you. Our next question is shifting focus away from CubeSats and going into your work as an astrophysicist, as well as your work as a professor of aeronautics. As somebody who would like to pursue a combination of astrophysics and aeronautic engineering, how did you find yourself balancing both the theoretical aspects that come from astrophysics as well as the physical aspects that come from aeronautics?
Good question. First, I'll talk about my path there, then I'll talk about the balancing. Well, it's important to become an expert in one thing. That's why as an undergrad, you have a major. But as an undergrad, you can also have a minor. So I think the idea is to pursue one thing in depth, but you can still carry another interest along as you go. The good thing about getting older is knowledge is cumulative. So you can have your major expertise and then later on build up that minor to become a major. Also, when you're older, you don't necessarily have to go to classes, although classes help, especially. I bet everyone uses online tools. Like you can use ChatGPT-4 is really good for learning, I've heard, because it can explain things, or you can take Coursera. You can do a lot of things. So when you're older, you can learn by doing research and then by supplementing with online educational tools. So the important thing is focus on one thing, but as time goes by, you have time to branch out into those minors. Balancing is not too hard as long as there's a lot of overlap. So astrophysics and space engineering may seem very different, but a lot of the equations are the same. We have Newton's laws, we have differential equations. I'm trying to throw things out there because I know when you're studying, it's like, how's this ever going to be useful? Like differential equations are used everywhere. So there's a lot of overlap in the fundamentals, but sometimes the language, and it's not just the language, but the philosophy is so different, like the way people's brains work and how they operate. Those are very different. So balancing is more, believe it or not, it might sound really strange, but it's being socially aware of like how different cultures in engineering versus astrophysics versus other things work so that you can all try to work together.
Thank you. Could you go a bit more in depth about the mindset that comes from the different fields, astrophysics versus engineering?
Mm-hmm. So for example, one thing we do in working with engineers, and that can be on either side of us, we have our science goal,
Mhm.
which we have to translate into a science requirement. So I might want to say, I want to find another Earth, but that doesn't help you engineers at all. I have to say, look, I need to be able to measure. I need to be able to block out starlight to 1 part in 10 billion for a star of a specific brightness at a specific on-sky projected planet-star separation. So we go from science goal to requirement to engineering requirement. And then we keep going down. So it's like a specification of what you've got to fabricate. It's actually really hard to make that. But one of the cultural differences is, in engineering, you might say, well, I can't do that, but I can do this other thing. Because you've just got to get the job done. But that other thing might destroy the actual science somehow. So there's that. And in science, we're always trying to be more greedy. Like we want more data, we want more of this or more of that. So sometimes in science, we just want to answer the question. And an engineer, it's sort of like the practical reality of what you can do. And so the mindset tends to be very different there.
Thank you. That was really informative.
Yeah, in fact, one of my favorite classes I ever taught, it was a design and build class, a capstone undergraduate aerospace engineering class, and it was project based. And for the first time, we brought in the science students. So like it's divided into subsystems. So you'd have like mechanical or thermal or structural. And it was really interesting because it took a whole semester almost for the students to be able to talk to each other. Because the science students were like, you should have taught us how to talk to the engineering students, just what I was saying.
Mhm.
But that was obviously part of the exercise.
So, would you advise for science students and engineering students to kind of maybe take some classes in the other field? That way they can help bridge the gap in communication?
I think it might be more like research, small research projects, mini projects, because in the class, it's all quite similar. Like you're going to learn the equations, you're going to get problem sets. So in this class, it was like hands-on. It wasn't maybe so much research as implementation. But yes, I do think having some mini projects or activities together could really help a lot.
Yeah, thank you. Moving away from astrophysics in that regard and moving into your research in exoplanets, what conditions do you look for when you're going about finding exoplanets? Are you searching for a twin Earth, or are you searching to catalog the different types of exoplanets that exist in the universe?
I would say all of the above. My dream is to find a twin Earth. My dream is to find a twin Earth, an Earth-sized planet in an Earth-like orbit about a sun-like star. And it's not like an Earth out there nearby. It's not fainter than the faintest galaxies we've ever observed, but it's right next to a big, bright, massive star. So any technique we need to use has to deal with the star. And right now, our Earth is just too small and too faint and too low mass to find an Earth twin. It's like if you wanted to find your identical twin.
Yeah,
Well, it might not exist, but it would be so cool, wouldn't it?
would
Okay,
be.
but that's kind of not happening. So maybe you'd be more happy with finding a cousin. Maybe this cousin is like a different generation and maybe they live in a different country, but still should be cool, right?
Mhm.
Not as cool. So we're kind of focused on what we can do right now, which is finding Earth cousins. And these so-called Earth cousins, I like to call them, they're small rocky planets, but they're orbiting M dwarf stars, small red dwarf stars that are half to 1/10 the size of our sun. And they're very, very different. Like the planet around the M dwarf star, if it has to be quite close to the star to have the right temperature for life, because the stars give off very low lumen energy output. But what happens is they're so close that due to tides, the planet gets into a very special low energy configuration. It rotates one time for every time it orbits. What's so mean is like 1 day equals 1 year. Actually, our moon does this. Due to tides, our moon shows the same face to Earth at all times. And people don't often realize it means it's actually rotating at the same rate that it's orbiting. But what this means on those such planets, if we could be on one of those planets, the star or the sun would be in the same place in the sky at all times. It would literally not set or rise. But you could travel to another location on the planet and see it always setting, or you could go where it's always night. Unfortunately, these stars, they have a lot of flares and spots, and they give off a lot of energy, actually.
Mhm.
So life there would have to be quite different. They might live underground to be protected from the harsh radiation. I'm not sure where you're located, but here in Massachusetts, we get this wonderful thing, giant snowstorms, and like everything will close and you get to stay home. I'm not sure if you've ever had that. It's so fun.
Definitely
Yeah.
during the nor'easter season in New York, we get
All
that.
right. Yeah. They tried to cancel snow days once Zoom was a thing for kids in school, and everyone just pushed back. Yeah, because everyone needs a fun break. It's like, yeah. But I imagine on these other planets, if there is intelligent life there, I'm guessing they have radiation days when they have like a giant burst from their star and it hits their planet and they get a big aurora and they get charged particles. They probably have to stay in their basements for a few days, just to let it all dissipate. So the planets are very different. Nonetheless, it's what we can study. And myself and a lot of other people, we're in the process of understanding these objects with the new James Webb Space Telescope. Do they have atmospheres? If they have atmospheres, do they have signs of water vapor, which might mean there's a water ocean, which life needs water? So it's a really cutting edge time right now.
Definitely. Um, to that point, another question I have is, what does it look like when you try to analyze the atmosphere of a planet? Are you looking for something specific? Is it like a light spectropsy that you do?
Yeah,
Or
it's definitely light spectroscopy, but actually our data is pretty noisy right now. So Like an analogy is like having a very grainy image and sometimes trying to find out what parts of that image are real and what parts are artifacts.
Mhm.
And if you can convince yourself it's real, or sometimes the signal is very strong and it's robustly real, you have to attribute it to a molecule. It's like, yeah, but I can explain it a bit more. We have a special set of planets that are perfectly aligned. They go in front of their star as seen from our viewpoint, and we call these transiting planets. And when the planet is front of the star, some of the starlight shines through the atmosphere. So if we look at the star alone, and then if we look at the star when the planet's in front of it, we can subtract that and we can understand what's in the planet atmosphere, because the planet atmosphere blocks some of the starlight at distinctive wavelengths. And we use that blocking along with like libraries of molecular databases to try to find out what molecules are doing the absorbing and hence which molecules are in a planet atmosphere.
Very impressive.
Yeah.
Are there any other methods you use when trying to discover exoplanets? Is it mainly just transiting or?
No. In fact, I don't even know if you remember a day when there would be like the ice cream flavor of the month,
Yes.
probably just trying to sell the ice cream more. Like for exoplanets, we literally have like, think of it, the flavor of the decade, if you will. So way back when exoplanets were first discovered, there were no transiting planets. They require fortuitous alignment because they'll have any orbit, or any, yeah, very few transit. They have to be lined up just so. If the planet is orbiting in the plane of the sky, you'll never see a transit. So originally there was a completely different method. We call it radial velocity or the wobble method. A planet and star orbit their common center of mass. So a star appears to wobble if there's a planet. It wobbles, like in the period of the planet, yes. And we can actually measure the line of sight motion. It's kind of too complicated to summarize in 1 minute, but let's just say there'll be like a new technique that comes into play each decade as new telescopes come online, as technology gets better. And so, if we were having this conversation 10 years from now, we'd be talking about something else, a different technique. Yeah.
Thank you. Speaking on how technology can help advance the study of exoplanets, where do you think the focus on technological advancements should be placed? Should it be placed on creating better telescopes like the James Webb Telescope, or just in getting more materials into space?
Well, everything, all of the above. I mean, one thing that helps is detectors. You know how probably every person your age has a phone. And even if you have an old phone or like a really cheap one, your camera is surprisingly good. Like think about that for a minute. That's because technology and our detectors got better and better and small, we can have smaller and smaller electronics. We want our detectors to get better and to have less noise. Like, if you try to take a picture in the dark and it's really hard because you have to hold it. So getting better detectors, not just for astronomy, that will develop anyway, is really important. As to space, what's really interesting is eventually we need a new way of doing things. So getting materials to space, people have dreams of manufacturing in space. And that would be really a game changer for us. Because if you think about space rockets that go to space, some of them are huge now, but they're still limited in the size of the telescope you can put up there. The Webb folded and then it had to unfold, but even you can only make so many folds. So if you could have a way to self-assemble in space, that would change things for generations to come.
Thank you. I remember looking into this a couple years ago, the idea of creating a very large telescope or having multiple telescopes set up on the moon. Do you think that that could be a possibility? Is that something that we should be aiming towards, or do you think it would be better to, at least in the short term, place effort on what you were saying earlier, manufacturing in space?
It's really a great question. And it does seem like, okay, you could go to the moon, you could set things up. But honestly, when you think of astronomy, the moon isn't for just regular, sort of like conventional astronomy at visible wavelengths. Space is just great. I mean, the moon has a lot of dust and it's not necessarily super practical for visible wavelength astronomy. People really like it, the idea for radio astronomy, for putting really large radio telescopes there or arrays of them, because it also blocks out from any radio interference that's here right now on Earth.
Thank you. Going back into the search for alien life, we talked about you earlier. You talked about there being a different kind of lifestyle that they would have to live on different planets. Um, how would that change for each planet? Like, say, a planet that wasn't orbiting around a red dwarf.
Like, we don't have a full answer to that question right now because we don't really understand the origin of and evolution of early life on our own planet Earth. So it's really interesting project. Like here, you know how we humans were just so vulnerable? Like if you cut off our oxygen supply or even decrease it a bit, we'll just die. Or you know how people get carbon monoxide poisoning? They get a little more of this, a little more of that. But you know, there's some very simple life forms. They don't seem to mind what their air is made of. Like little tiny bacteria, E. coli. You hear about them sometimes because they like, you know, you get food with E. coli and then it poisons you. Not too badly, but you know, so there's some bacteria that they're not so complicated like we humans are, but they can survive with almost any type of air as long as they have the right nutrients. Some bacteria are especially radiation tolerant. Maybe that type of life would exist on a planet that gets bombarded by radiation. I mean, we do study life in extreme environments on Earth. Scientists go to remote regions, very dry, very acidic, very salty, and they, you know, pick up some bacteria and try to study it in the laboratory. But honestly, these exoplanets are probably way more extreme than the most extreme environments on Earth. So I don't even have a good answer. That's why I'm rambling. We don't have a good answer. We just know that pretty much anywhere on Earth where life can exist, it does exist, simple life. And that we assume that life out there has to be using chemistry like we do to extract energy from the environment, to store energy, and eventually to use energy.
Thank you so much. Those are all the questions I have. If it would be okay with one more question to close out
Oh,
everything.
yeah. And I also have one more final statement too.
Perfect. The question is, what advice would you like to give to those in general, those in college, those in postgraduate school, everything?
I do. And that was what I wanted to say as well. I'm a big believer in the power of positive thinking and in building confidence. And those two are highly related. So I really want everyone to develop your inner voice. You know, like if you're in a dark alley and there's a shady figure, like that's a bad feeling. That's your inner voice saying, like, get out of there. But you can also use that inner voice for good feelings. If you're exposed to a new subject and you really like it, you should try to do something about that. Talk to your professor, read more about it, take opportunity. But building confidence is so important because there'll always be your surroundings and sometimes even yourself that chips away at that by using like that negative voice, like, no, I can't do that, or this is awful. You have to take some time every day to pause for a moment and think about your win for that day, no matter how big or small, and spend as much time like being nice to yourself or reflecting on positive things as you do on negative things. So if you do badly on a test or you have a bad presentation at work and you're like, wow, that was awful. Okay, I mean, that's okay. That's going to happen. But when do you spend the time saying, I did amazing? I kicked ass. When do you say that? Well, you should be saying that more often than you're saying the bad things to yourself. And that's especially true if you're in an environment where people, you know, you're the new person at your job or at school and people aren't sure about you. You have to walk in there thinking about your past and reflecting on that. And that's your key to your future.
Thank you so much, Professor Sager. That concludes all of our questions. Thank you so much again for taking the time to speak with me and to speak with the I5 community. We really appreciate it.
Thank you. My pleasure.